We will not meet on Monday, but I'm going to open all the quizzes, okay? Starting Monday, and you have until Saturday next week to what we call retake it. So you can retake all 10 quizzes, but I'm going only to look at the highest scores, okay? And the one where you have the highest scores for the first attempt, which I already recorded, and the one that you have the highest score in the lowest part of questions yet. But all I can say is just take all the quizzes again. Okay, so I have numbers to look on to improve your uh, grade in this class. So just take advantage of that thing. So today we're going to talk about the gases. So if you remember in our first chapter, gases are what? Okay, gases are state of matter that has no definite shape and no definite volume. Okay, we say gases are compressible, and the main reason for that is since they have a lot of space in between them, you can compress them. Okay, the gases can occupy the large space in between them. So that we could say is the main difference of gases from liquids and solids. They are compressible. They can be compressed. Now, if you're going to look at the properties of gases, okay, all of them has pressure, they have volume, they have temperature, and the amount. And if you're going to look at these four factors, okay, or four variables, you could say that they are all related to one another. And what we're going to do today is we're going to discuss some of the natural laws about the gases. Now, it's just so odd that among the three physical states, okay, or among the three states of matter, gases is the one that has the most number of natural laws. Okay, and you will have some of them today. And if you're going to take your Chem 112, you're going to know more about the different gases or the different natural laws for gases. Okay? They are the most studied, even though you don't see them most of the time, because most of the gases, but not all gases, just wait for that. Most of the gases, but not all gases, are, we could say, colorless. Some are even odorless, okay, but not all. It's just most. Okay. Now, if we're going to look at some of the properties that gas exhibited, I think the first one that we could look at is pressure. Okay. So if you're going to look at the pressure, this is just the force exerted per unit area. So usually the word pressure, we can associate it with our everyday life. So like right now, your pressure to finish the course, okay? So if you're not doing that, your pressure to study and hope you get better when you take the quiz again, okay? So pressure can be given by two equations. It can be given as this. Pressure is equals to force per area, or it can be given like this one. Pressure is just equals to the density times the gravity times the height. Okay? And if you're going to look at the unit that are involved in this, what we call two equation, one we could say kilogram times meter per second squared over meter squared. And if you're going to what we call make an operation for this one, you will end up with what? Kilogram meter, kilogram per meter times S squared. Now, if you're going to look at the pressure from this other equation, you could have kilogram per cubic meter. So that's the density times gravity, okay, due to acceleration. So that's meter per second squared. And then height, which is just equals to meter. So if you're going to look at this one, you will just have kilogram per meter times second squared. And if you shorten that, that's just your Pascal. So the unit, the SI unit for pressure is Pascal. But there are other units, and usually they are more popular than the SI unit. Okay? Oh, some of the common pressure units are the following. So you have the atmosphere, which is denoted as ATM. You can also have millimeter mercury, you can have torr, and you can also have bar. So if you're going to look at the equivalent of this unit with one another, so if you have Pascal, okay, that's kilogram per meter second squared, or kilogram per meter second squared, yep. And if you're going to look at atmosphere, so one atmosphere is around 1.01325 times 10 to the 5 Pascal, or 101 kilopascal. Now, millimeter mercury or torr, if you look at the history of that, okay, so they found out that every 1 atmosphere pressure, okay, the height of the mercury is around 760 millimeter. And it was determined by Evangelista Torricelli, which is where the torr word came from. Okay. Now for the bar, okay, it just says that if you have 1 atmosphere, is equivalent to around 1.01325 bar. But the one that is commonly used is atmosphere. And next to that is the millimeter mercury. So 1 atmosphere, okay, is equal to 760 millimeter mercury, and that is also 760 torr. Okay. Now, the device that measured the atmospheric pressure is called the barometer. Now, if you want to measure also the pressure, if you have a gas or a liquid in a vessel, if you don't have a barometer, you can also use this so-called manometer. Okay. Now, to give you the idea about how Evangelista Torricelli did first measure the atmospheric pressure, so what he did is he had a mercury liquid in a container, and what he did is he put a vacuum glass there, and when he did that, he found out that the height of the mercury is around 760 millimeter. Okay. So we're not going to do calculations like this here. I'm just telling you how Evangelista Torricelli was able to revolutionize the measurement of atmosphere using mercury. Okay. Now, as I have told you, the gases has the most number of natural laws. And we call this empirical gas laws. Now, all gases behave quite simply with respect to the temperature, pressure, volume, and molar amount. So what they observed, by holding 2 of these physical properties constant, it's become possible to show a simple relationship between the other 2. So if you keep 2 out of 4 constant, you can see the relationship of the other 2 properties. Okay? And I think this is the first time that they applied the so-called scientific method. way back mid-17th century. Okay? In fact, the first one who studied this natural law, Robert Boyle, he revolutionized scientific method. Okay? He wrote this treatise called The Skeptical Chemist way back during his time. Okay? So there are a lot of empiricals that developed from mid-17th century to the mid-19th century. So if we're going to look at how Robert Boyles developed the Boyles Law, what he did is he just looked at the relationship between pressure and volume. Okay? So he found out that the volume of a sample of gas at a constant temperature varies inversely with the applied pressure. So what does it mean? When he applied pressure, the volume become less. Okay? When there's more pressure, the volume is less. If there is less pressure, the volume is high. So this is the mathematical relationship of the Boyles law. Okay, the Boyles law just states that the volume of the sample of gas is inversely proportional with pressure at constant temperature. And if you're going to put it in the equation form, okay, so P times V there will give you a constant value. And if P times V there will give you a constant value, that means you can relate initial pressure and initial volume with final pressure and final volume. So what does it mean? At constant temperature, okay, the pressure is inversely proportional to volume, or volume is inversely proportional to pressure. And if you're going to look at this one, you're going to do an experiment of this, if I'm not mistaken, next week. And experiment 8 is the last experiment, okay? We're not going to do experiment 9. We replace experiment 9 with the home experiment, okay, that we're given to you, okay? And out of the 11 experiments that you're going to perform, I'm going to drop the lowest one there, okay? So figure A shows the plot of volume versus the pressure. So 1 gram of oxygen at 0 degrees Celsius. As you can see here, it's non-linear. But if you're going to get, instead of the volume, you get the inverse of the volume, you could see the relationship that they have there. It becomes linear. But in the sense that it's an inverse relationship because you get the reciprocal of the volume. So what does it mean? Okay, as you increase the pressure, you increase the reciprocal of the volume, or as you increase the pressure, the volume decreases. Okay, so you have it in your experiment, the what we call values of pressure and the corresponding volume that you have. Okay. Now, another way of looking at this is using the so-called J tube. So at 1 atmosphere, the volume is around what? 100 ml. Now, when you double the pressure, the volume is half. Why is it 1/2? So 1, and then you make 2. So 1 will be 1/2. Then if you triple it, okay, the effect will be 1/3. Because there's an inverse relationship between volume and pressure. Okay? Now, if you're going to look in terms of piston, the gas pistons. So here you just apply what? 0.5 atmosphere, and the volume that you have is 1.40. Now you double the pressure, what will happen? The corresponding volume is 1/2 or half. 1/2 of the original volume. Okay? Now, let's try to solve problem with regards to this one. So a volume of gas or oxygen gas occupies 38.7 ml at 71 millimeter mercury and 21 degree Celsius. Now you are asked what is the volume of the gas if the pressure changes to 359 millimeter mercury while the temperature remains constant. So what you're going to do here is maybe assign, okay, the information given to you. So you can put B1 as 38.7 ml. Pressure 1 is equals to 751 millimeter mercury. Now, as you could see there, there's also a temperature that's given, but you can just ignore it, okay? And instead you put there the second pressure, that's 359 millimeter mercury, and the one that you're looking for, which is B2. You just let this ambulance pass through. Okay, so as you recall, we have P1 equals B1 equals to P2 over B2. Since we're looking for B2, we can just divide both sides by P2. So you don't need to convert these values here because if you're going to plug them, so 751 millimeter mercury times 38.7 ml, and then you divide it with 359 millimeter mercury, as you could see, you can just cancel the units that are found in both numerator and denominator, giving you the final unit as the unit of volume. And you can predict, okay? So this, since the question that we have, even for calculation is multiple choice, sometimes you don't need to do a calculation. You can predict it right away. So you could say from 751, the pressure, okay, decreases. So most likely, what will happen? The volume will increase. And to check that, you multiply 751 with 38.7 divided by 359, and you get there around 80.96, or if you're going to round it up, you will get a value of 81.0 ml. So as you could see there, three significant figures, three significant figures, three significant figures. So the final answer would be three significant figures. Okay, it's 80.957 if you're going to look at the calculator. But since you have to finalize it in such a way, you're going to have to write it in three significant figures. You round it up to 81.0. Check, because you're going to have questions like this in your chapter quiz, and maybe chapter in your what we call final exam. Okay. So the final exam, you should be able to take it on our last meeting, if I'm not mistaken, July 12th. Okay. So it covers everything. That's why what I want to do is when you retake the quizzes, I'll give you maybe until Saturday, and then I'm going to make all the answers on your quizzes available as you review for your final exam. Okay? Now, another thing that we can relate is the one that we have here in this plot. So we have temperature with volume. So when they graph volume versus temperature, they found out it's linear. Whatever the gas identity is or whatever gases you have, they always cross line at zero volume. And they end up with the temperature at negative 273.15 degrees Celsius. So they designated the temperature at negative 273.15 degrees Celsius as the absolute zero. So it is the temperature at which the volume of the gas is hypothetically zero. And this is the basis of the absolute scale or absolute temperature scale, which is the Kelvin. And this is not new to you. We discuss about the different units of temperature. We say Kelvin, Celsius or centigrade, and what we call Fahrenheit. And in addition to that, there's also some books that mention the unit called Rankine. Okay. Now, the temperature and the volume relationship in terms of gas, that's the basis of Charles law. So Charles law, okay, states that the volume of a sample of a gas at a constant pressure is directly proportional to the absolute temperature. So what does it mean? Volume increases with increase in temperature. Okay. Now the main thing that Charles observed that is because he's fan of this so-called balloon, the one where you can ride in the balloon. So he's a French guy. So that's what they usually do. So based on his observation, he studied that if, okay, you increase the temperature, the volume of that gas will increase. So this is the relationship that they have. And if you're going to look at the constant here, so B over T will give you a constant. And from that constant, you can establish a relationship where the initial volume over the initial temperature is equals to the final volume over the final temperature. Proof that this relationship is really true is this one. So when you put your balloon in a liquid nitrogen, which is really low in temperature, you could say the amount of volume that you have here. If you want to do a home experiment on that, I would suggest you put an empty water bottle in the freezer, and what you could see, okay, it will deform. It's just like it sucks something out of itself. Okay, but the main reason there is the gas that you have there, their volume decreases. See, if you allow it to just be in room temperature away from the liquid nitrogen, what will happen is the volume will increase because the temperature here is different or higher compared when you put the balloon, okay, in liquid nitrogen. So that's, we could say, the proof of this Charles law. Now, when the temperature of the sample is raised to 200 Kelvin, the volume of the oxygen is doubled. Okay? And a 1 gram sample of oxygen at a temperature of 100 Kelvin and a pressure of 1 atmosphere usually occupies a volume of 26 liter. Okay, so you could see the same pressure, the only difference is the temperature. You increase the temperature, okay, you increase the volume of the said gas. So if you're going to look at this, if you have a problem like this one, you prepare the carbon dioxide by adding HCl to marble chips, which is calcium carbonate. According to your calculation, you should obtain 79.4 ml, okay, of your CO2 at 0 degrees Celsius and 760 millimeter mercury. Now, you are asked how many ml of gas would you obtain at 27 degrees Celsius? I would say you can list down everything here. B1, you have what? 79.4 ml. T1 or Ti, you have 0 degrees Celsius. Now, you don't know what you have here, but T2 is you have 27 degrees Celsius. Pressure is just the same at 760 millimeter. Now, what the thing that you need to make sure when you do calculations here? You have to make sure that your temperature is in Kelvin. So it's easy. You just add them with 273. Okay. So you have here 273 and you have here 300. Now, once you have that, you plot the relationship that they have. So it's what? If you look from the previous slides, it says there B over T. So B1 over T1 equals to B2 over T2. So the one that you're looking for is the volume. So you just multiply both sides by T2. And if you have that, you will end up with B1 T2 over T1. And that is just replacing the value that you have there, 79.4 ml times, this should be a T2, which is 300 ml. No, not 300 ml, 300 Kelvin divided by 273 Kelvin. Now you can deduce it right away. So 0 degrees, 79, 27 degrees Celsius. So that means you should have a higher volume. And that would be equals to what? 79.3 or 4 times 300 divided by 273. So you have there 87.3. So I want you to analyze this type of problems because these should be sure points when you take our what we call chapter quiz later this week. Okay? And if you are asked, if you're given the equation, you just be given a general equation for this one. And from that, you should be able to, we could say, deduce what the equation would be. Okay? So what we have done so far is relate pressure with volume and volume with temperature. Now, what if we combine the three? So if we combine the Boyles law and the Charles law, we're going to have a mathematical relationship like this one. Remember, volume is inversely proportional with pressure, okay? And volume is directly affected by temperature. So volume is inversely proportional with pressure and volume is directly proportional with temperature. So you will end up with this relationship. Because if you're going to do, how do we end up with cross multiply of P and then divide by T? So you end up at that one. So if it's a constant, so this means that you can look at the relationship in pressure, volume, and temperature. If you know at least 5 of them, you can determine the 6th one. So if you're given the initial pressure, initial volume, and initial temperature, and you're given the final pressure and final volume, you can determine the final temperature. If you're given the other two, you can determine the third one. Okay? So for instance here, scuba diving problem. So divers working from a North Sea drilling platform experience pressure of 5.0 times 10 to the 1 atmosphere at a depth of 5.0 times 10 to the 2 meters. So if a balloon is inflated to a volume of 5 liter, which is the volume of the lung at that depth at a water temperature of 4 degrees Celsius, what would be the volume of the balloon on the surface at 1 atmosphere and a temperature of 11 degrees Celsius? So the way that you're going to do it is just line up the info that you have. then what you're going to do, you put what's given there. Okay, so you can put, let's say, the volume of the balloon, 5 liters. And that corresponds to what? Temperature of 4 degrees Celsius. And that would have what? 5.0 times 10 to the 1 atmosphere. And all you need to do is just convert this to Kelvin. So that will be 273 plus 4, 277 Kelvin. And then in the P2, what do you have? 1 atmosphere. The volume is the one that you're going to determine. And the temperature is 11 degrees Celsius, which you're going to convert to Kelvin. And you're going to look at the relationship that you have. So you have what? P1 V1 over T1 equals to P2 V2 over T2. So what's the one that we're looking for? The volume. So that means you just have multiply both sides by this. You cancel this out, you cancel this out, so you have here. And you're going to replace the value that you have. No, P1, not 5. So you have here 5. Volume is 5. Okay. Temperature is, what do you have here? 284 K divided by 1 atmosphere, the P2, and the temperature 277 Kelvin. Now look at the unit. Kelvin over Kelvin, atmosphere over atmosphere. That's not -1, that's just 1. So you have there the unit that is in ml. And if you're going to look at this, you end up with 2.6 times 10 to the 2 ml. So you're going to get around 256, but you want to express them in two significant figures. So you round it up as 2.6 times 10 to the 2. Okay? Now, as you could see, you might ask yourself, Professor, at the beginning you said 4. Why did we only involve 3 so far? The 4 factors that we have, the Avogadro's law, that's the last concept that was known. Okay? So this concept was known after the mole concept was introduced. So who is the one in charge with the so-called mole concept? Okay, so the mole concept was introduced by Amadeo Avogadros. Okay, so when Amadeo Avogadro introduced the concept of the mole, so that's the time where you introduce also the relationship of the amount of the substance. So in the gas natural law, we call it Avogadro's law. Okay, so if we're going to look at this Avogadro's law, it just tells you the relationship of the amount, okay, of gas with the volume. Okay, so what does it says? You're going to have equal volumes of any two gases at the same temperature and pressure. Okay, so The way that you look at this one is it just looks at the relationship of N with T, not T, B, the volume. So what we have earlier, pressure inversely proportional with P, uh, volume inversely proportional with P, volume is directly proportional with T. Now in Avogadro's law, it states there that if the temperature and pressure are the same, okay, if you have equal volume of gas, it also contains the same number of molecules. And I want you to remember the so-called standard temperature and pressure. So this is the reference condition for gases chosen to be what? 0 degrees Celsius or 273 Kelvin and 1 atmosphere. So at this condition, they found out, okay, that the molar volume of gas at STP is 22.4 liters per mole. So 1 mole of any gases at STP will occupy 22.4 liter. Okay, and this is just approximately what? Bigger than a basketball. Okay, so if we're going to relate everything that we have so far, so we look at P with respect to what? The volume. We look at volume with respect to temperature, and now we look at what? Volume with respect with N. So if you're going to relate this thing here, that will give you a constant. Volume indirectly proportional with pressure, volume directly proportional with temperature, and volume directly proportional with N. So all of them will give you a constant. And you can assign that constant giving you, if you have a TB equals to NT equals to a constant, you can assign it, let's say, into R, giving you TB and RT. And that is what we call the ideal gas law. Now, if you're going to look at the ideal gas law, okay, so from this relationship that we have, we could say what? P1 equals to B1 and then over N1 over T1. And if you have here P2, B2, N2, T2. Now, if you're going to look at the Boyles law, so that means constant moles and constant temperature. So what do you have here? P1 equal P1 times B1 equals to P2 over B2. Okay, you just cancel this out because they are both constant. So you have here the Boyles law. Now, if you have, let's say, P1 B1 N1 T1 equals to P2 B2 over N2 T2, if we want the Charles law, so that means constant pressure and constant volume, so you can derive the relationship there. So the one that I'm going to give you is just this equation, the ideal gas law. Now, in one of your experiment in gases, you are going to determine the value of the R based on the other values that you have. In general chemistry, you're going to use either this one or this one. We can simplify it as the 0.0821 or the 8.314. Now the question is, when are you going to use this value and when are you going to use this value? So this value is used for non-energetic problem and this value is used for energetic problem, or one that involves energy because of the unit joules. Okay? Now, if you're going to look at the PV equals to nRT, you can find, okay, that you can put it like a constant, some of them. So here you can just use, we could say, the relationship between the moles of a substance with a given pressure, provided that P and T are constant. So based on this, what can you say? Okay, you can say that the amount of gas is proportional to the pressure at constant temperature and volume. So what I'm trying to explain here to you is, with the ideal gas equation, you can derive the other natural laws of gases. And the ideal gas equation also, or the ideal gas law, can help you determine if three factors or three variables are given, you can determine the fourth one. And there's a lot of, we could say, derivative calculations that you can do using the ideal gas equation. Okay? So if you have a 50-liter cylinder of nitrogen that has a pressure of 17.1 atmosphere at 20 degrees Celsius, so what is the mass of nitrogen? Or maybe let's try to make this different, because you already have this in the recording. So instead of nitrogen, we put it oxygen. So that you just don't need to repeat everything when you watch the video. So you can have other, what we call, means to differentiate the problem. Okay? So if you're going to look at this, maybe you can start from this one. And what's the being one that is being asked? The mass. Now you don't see the mass here, okay? But you know, moles is equals to mass over molar mass. Okay? Now you can rearrange it in such a way you will end up with this one. Or you can put that one. So you replace the n here, leaving you with mass equals to pressure times volume times the molar mass over RT. Okay? Maybe we can do this one here. So the given pressure that we have here, 17.1 atmosphere, and then we have 50 liters, and then we can use the 0.0821 liter atmosphere K mole, and then the temperature which we're going to convert to Kelvin. No, that's 273. No, that's just 296. So if we have this 17.1 times 50 divided by 0.0821 divided by 296. So you will get around 'Now look at the unit, atmosphere. cancelled atmosphere, liter, cancelled liter, Kelvin, Kelvin, giving you mole. Now we're not done because we are asked for the mass. Now this is oxygen. Oxygen is how much? 32.0. Ah, so 35.18 moles times 32 grams per 1 mole. So that will give you 17.1 times 50 divided by 0.0821. I have around 1,000. Now 1 point, that's at 1 point, that's 1.13 times 10 to the 3. That's oxygen. Now what I want to do, okay, what if I use this one? So 17.1, 50, and then I will, there are 32 grams per mole divided by 0.0821 liter atmosphere K mole, and then you have the 296 Kelvin. And if you're going to look at this one, so 17.1 times 50 times 32 divided by 0.0821, okay, divided by 296, and you're going to get also the same amount at this one. So as you're going to look at this question where you are asked the mass based on the ideal gas law, you just modify that thing, the ideal gas law. Now you can also do some modification using the ideal gas law if you are asked for the density or the molar mass. Okay. So if you're going to look at this is the one that you have. But I'm going to show you how they end up with that one. Because instead of memorizing this, you can derive it from the given one. So for instance, you have what? PB equals to nRT. So what are we going to do? Okay, N is equals to mass over the molar mass. So we're going to replace it there. And then cross multiply. So if we want to get the derived equation or formula to determine the density, all we need to do is put this one side in density, and density can be equals to what? Mass over volume. And if you put it on that side, you cancel this out. And if you want to leave this here, what will happen? You multiply both sides by 1 over RT. And in doing that, you will have P molar mass, pressure molar mass over RT equals to mass over volume, which is your density. Now I can also go in such a way I want the molar mass on one side. So from here, what will happen? PB molar mass MRT, and then I just divide both sides by PB. So molar mass is just equals to MRT over PB. Or we could say this M over B here is just equals to D. So you end up with this relationship here. And that's just the same as we have here. So ask yourself, do you think you can derive this one? Or you want this to be given to you? So all of this was derived from this. So let's try to solve a problem. So what is the density of methane gas given the temperature of 125 degrees Celsius and 350 atmosphere? So as I've told you, I don't know the formula. So what I do is I'm going to derive the formula. So the one that's being asked is density. So I have to divide both sides by B, and I have to multiply both sides by RT. So I now need to supply what I have here. Okay, 3.50 atmosphere. And then molar mass is given here. So that's around what? 12 plus 4. We could say around 16.04 grams per mole. And then divided by R is a constant. So that's what? 0.0821 liter atmosphere K mole. And then 125 plus 273 to give me Kelvin. So look at the units. This can cancel out. This can cancel out. Atmosphere can cancel out. So you end up with a unit that's grams per liter, which is a unit of density. And you're going to get around 1.72 grams per liter. Okay? So that's the density problem. Like, what about the molar mass? Like this one. You have a 500 ml flask containing a sample of octane placed in the boiling water bath in Denver, where the atmospheric pressure is 634 millimeter mercury, and the water boils at 95 degrees Celsius. So the mass of the vapor required to fill the flask is 1.56, and you are asked, what's the molar mass of the octane? And you're also given here that the empirical formula of octane is C4H9. So you are asked, what is the molecular formula of the octane? So we're going to look at the one that we derived earlier. we have this. So we have molar mass, okay, equals to MRT times PB. Now we can do here, what's the mass? The mass is 1.57 grams. The R is 0.0821 liter atmosphere K mole. The temperature here is 95. So 95 plus 273. So that's what, 365? Divided by, now you have here a 634 millimeter mercury, which you need to convert to atmosphere. The 760 millimeter mercury per one, no, it's 1 atmosphere over 760 millimeter mercury. So that's the pressure. And the volume that you have here is this one. So you just put it as 0.5 liters, because from 500 ml you convert this to liters. So you do the operation here, or you could look at what's the unit that we can cancel out: millimeter mercury, atmosphere, Kelvin, liters. So you end up with what? Grams per mole. And you end up with 114. Now, you already answered the question here, but then you still have a next question there. What is the formula or molecular formula of octane? And you're given here the empirical formula. So you have 114, if you recall empirical formula, that's the simplest whole number ratio. So you get the empirical mass of this one. So that's 4 times 12 will give you 36 plus 9. So 4 times 12, that's 48 plus 9, that's 57. So 114 divided by 57 will give you 2. So that means you multiply everything here by 2. So this is your molecular formula. So where did I get the 57? I get the molar mass of C4H9. And then I divide the molecular mass with the empirical mass to give me N, that's 2. So that's the multiple that you have to use to multiply in your empirical formula to get your molecular formula. Okay? Everyone there? Just checking out if you're still okay. I know the weather here in New York is really hot now. So I want you to work on problems like this because you're going to have, unlike chapter 10 where you don't have any calculations, chapter 5 and chapter 6, you have what we call calculations. And the next thing that I'm going to do here is relate stoichiometry with gas volume. And central to this one is the ideal gas law. So you can use the ideal gas law to find the moles from a given volume, pressure, and temperature, and vice versa. So problem that I have here is what? When a 2.0 liter bottle of concentrated HCl was spilled, 1.2 kilogram of calcium carbonate was required to neutralize the spill. So what volume of CO2 was released by the neutralization at the 735 millimeter mercury and 20 degrees Celsius? So how are we going to solve this one? So this is the one involving stoichiometry. So that means you need to write the reaction between what happens. So I can put here calcium carbonate reacting with HCl. And what does it produce? Calcium chloride, water, and CO2. Because the ones being asked is how much CO2 was released when you have 2-liter bottle of HCl reacting with 1.2 kilogram of calcium carbonate. So the next thing that we're going to do, maybe if we're going to look at the info of CO2, the one that was given there, the pressure and the temperature. So that means we need to know at least one more variable that we can get. Since volume is the one that's being asked, we need to determine how many moles of CO2 was produced. And we can do it using the calcium carbonate. So you're given what? 1.2 kilogram of calcium carbonate. We can convert it to what we call grams. So 1,000 grams is equals to 1 kilogram. And then from that, we can convert it to moles. Okay? So for every 1 mole, you have 100.09 grams of calcium carbonate. And based on the stoichiometry, what can we say? For every 1 mole of calcium carbonate that reacts, you have 1 mole of CO2 that is produced. So if you're going to look at the unit here, this is canceled out, this is canceled out, this is canceled out. So you have there the moles of your CO2. And you can calculate it. So we have what? 1.2 times 1,000 divided by 100.09. So you have it around 11.99 moles. Once you have that, you can do a PV equals to nRT. And what's being asked? The volume. No, not volume. P. Then you put the number that you get there. 0.0821 liter atmosphere. Okay, mole. And then the temperature, so 20, you're going to convert it to Kelvin. So that is equals to 293 Kelvin. And then divide it by what do you have here? 735 millimeter mercury that you need to convert to atmosphere. So this cancelled, atmosphere is cancelled, Kelvin is cancelled, mole is cancelled. So the final answer is in liters. 11.99 times 0.0821 times 293 divided by 735 divided by 760. So I have around 2 point or 298 liter. Or I could put it 298 times 10 to the 2 liter. So this we could say is challenging problem. Okay? The next topic that we have here is something to do with gas mixture. So what happened when you mix gases? It's rare that you see when you mix gases that there will be a reaction. Okay? Usually when you mix gases, each of the gases in the mixture retain their identity. So what John Dalton observed that in a mixture of unreactive gases, each gas acts as if it's the only gas in the mixture as far as pressure is concerned. So what does this mean? Okay? So if you have two gases here, initially you didn't mix them, and what happened? You force the gas to leave this plus A to go to plus B. Okay? So when they are not mixed yet, the pressure exhibited by gas A here, which is helium, is 152 millimeter mercury. And the gas that's exhibited by hydrogen on another vessel is around 608 millimeter mercury. Now, if you evacuated the gas in plus A and force it to go to plus B, the original pressure that is being exhibited by the gas when they are on their own, it's just the same when you mix them. The only difference now is since all of the gases are here, so the pressure that you have here for this container is just equal to the sum of the individual pressure of gases. So this is what we call the law of partial pressure. So partial pressure is the pressure exerted by a particular gas in a mixture. Now the law of partial pressure by John Dalton, it's just that the sum of the partial pressures of all the different gases in a mixture is equal to the total pressure of the mixture. Okay? Now, how is this being exhibited? So for instance here, you have 100 ml sample of air that is expelled from your lung. And when they analyze it, these are the composition that it has at 35 degrees Celsius. Now you are asked what is the partial pressure of each of the component. So in doing that, you have to get each one of them. The partial pressure of N2, the partial pressure of oxygen, the partial pressure of CO2, and the partial pressure of water. And if you're going to look at this is still what? PB equals to nRT. So if you're going to look at the partial pressure, it's just nRT over volume. Now, in this case, the only one that's changing is the number of moles. Okay? Because the R and the T and the volume are all the same. Okay? So the one that's changing is just moles, depending on the gas that you have. So everything here are what we call the same. So we could say we just need to get the N here and everything here is the same. So N for N2 is what? 0.0830 grams divided by 14 grams per mole. And then we could put 0.0821 times 35 plus 273, 308 Kelvin divided by 0.1. So you can bring down everything here. So the one that's changing is just this one. Oxygen, you have what? 0.0194 divided by 18 grams per mole. And then you multiply them here. CO2 is just 0.00640 grams divided by 44 grams per mole. Where did I get the 44? That's the molar mass of CO2. And then water is just 0.0441 grams. Okay. And I have 18 grams per mole. And then multiply whatever you get there. So you end up getting this value. So this is 0.749. This is 0.153 atmosphere. And this is what? 0.0368 atmosphere. And this is 0.0619. And when you add them together, you get this pressure. It's just a little bit multiple calculations, but if you're going to look at here, you're just changing the moles of each of the gas. So let's try another one. So here, you're given that the partial pressure of air in the alveoli, which is the air sacs in the lungs, is as follows. Okay, 570 millimeter mercury, 103.0 millimeter mercury for oxygen. Okay, carbon dioxide, that's 40.0 millimeter mercury, and water vapor, which is 47.0 millimeter mercury. So you are asked what is the mole fraction of each of the component of the gas in the alveolar air. So what you're going to do, all you need to do is add everything there. 570.0 plus 103.0 plus 40.0 plus 47.0, and that's 760 millimeter mercury. And to get the mole fraction, all you need to do is divide each of them with 760. So 570 divided by 760, so you have here what? 0.75. 103 divided by 760, then you have here 0.1355. 40 divided by 760, you have here 0.0526. And 47 divided by 760, you have here 0.0618. And if you add them together, that will give you 1 mole. Okay? Now we can also have collecting gas over water. I'm not sure if we did this in the lab portion, okay? But usually these are common problem when you collect gases over water. So the result is a mixture of the gas and the water vapor. So the one exhibited there by the pressure, that's not the pressure of the water, because water in liquid state, it doesn't have pressure. The pressure there of the water is when it is in gaseous form or as a water vapor. And you can apply law of Dalton's partial pressure here. The total pressure is equals to the sum of the gas pressure and the vapor pressure of water. The vapor pressure, that's the pressure of water in gas form. And you're going to learn about it in the first chapter of your Gen Chem 2. Okay? And usually the partial pressure of water depends on the temperature, and you should be given on that if you have problems like this one. Okay, so this is the what we call the pressure at a given temperature. So if you're going to look at it, the higher the temperature, the higher is the pressure. Because the higher the temperature, you're forcing water to evaporate. Okay, so if it's evaporate, you have there more vapor, so that means you're going to have more vapor pressure, or you have a higher pressure because you have more water in the gas form. Okay, so the way that they apply this Dalton's law of partial pressure, you have this reaction, zinc reacting with HCl, wherein you produce H2. Okay, now if you're doing this experiment, usually this is how you're doing this. So you have an HCl, you add it with zinc, it produces hydrogen. So what's the hydrogen do here? It produces bubbles, okay? And the bubbles would displace the water that you have there. So if you're going to determine here the partial pressure of the hydrogen with the water vapor, partial pressure, this is the value that you have. 752 for the hydrogen and 17 for the water vapor. Okay? Now, you may ask, how do you know you have 752 hydrogen? So, in a given temperature here, when they do the experiment at 19 degrees Celsius, the vapor pressure of water is 16.5. So, as Dalton's law of partial pressure said, okay, it's the sum, the total pressure is the sum of the individual gases. Now, you know, you are asked for the partial pressure of the hydrogen. Now, you have the total pressure. So, the total pressure is given as 769. And then at a given temperature, you're given the partial pressure of the water vapor. So, all you need to do is subtract it with the total pressure, and you will end up, okay, with the partial pressure of hydrogen. So usually this is pretty straightforward problem. But I don't give problems like this in your chapter quiz. Okay? But you might have a problem similar to that in this one. But I tend to neglect this one because you have already what we call the ideal gas law is really going to be the one that is needed. And then it's just a mixture of the other natural gas law calculation. So here, so this is a stoichiometry and a mixture of this low partial pressure problem. So you prepare nitrogen gas by heating ammonium nitrate. So ammonium nitrate, you have N2 and water. So if you collected the nitrogen over water at 23 degrees Celsius and 727 millimeter mercury, how many liters of gas would you obtain from 5.68 ammonium nitrate? So how are we going to solve this? So you're asked for the volume. So if you're going to look at the volume here, PV equals to nRT. So the volume that you have is just nRT over P. So R is known, temperature is given here, pressure is given here. So the one that you need to know is N. N. Why? You're given 5.68 grams here, and all you need to do is get the molar mass of this one, ammonium nitrate. If you're going to count that, that's 12. Okay, 4 times 1, that's 4. And then, no, not 12, 14. 14 plus 4 plus 14 plus 32, 16, 16. So if you're going to do that, you will end up with what? 13, 32 plus 14, 14, that's 28. So that's 60, around 64. So there you get the corresponding moles that you can use here. Okay? So you can get how many moles there? 568, 5.68 divided by 64. So you have around 0.008875 moles. 0.0821 liter atmosphere K mole. 23 plus 273 Kelvin. And then 77 millimeter mercury times 1 atmosphere, 760 millimeter mercury. Cancel the units that can be canceled. KK, moles, atmosphere. So you have their liters. So 0.08875 times 0.0821 times 3. Is it 300? No, it's 296. Divided by, oh, this is the thing. This is not 727 because you just need to get what we call the pressure of nitrogen. So it's not 727. So that's the thing that we need to determine. Okay. So what else information that we need to know here? So we need to get the vapor pressure of water at 23 that we have. 23, so that's 21.1. Okay. So total pressure is 727 equals to the pressure of the water plus the pressure of the nitrogen. So since this is what? 23 degrees Celsius, 21.1. So all you need to do is 727 minus 21.1. So you have the 706. So that's the one that you're going to use here. Because this 727 is the total pressure of the nitrogen with water. Now you need to get only the partial pressure of the nitrogen, which in this case is whatever the total pressure minus the pressure of the water vapor at the given temperature. And if we have that, 0.08875 times 0.0821 times 296 divided by 706 over 760, I get around 2.32 liter. I want to stop, but usually when I stop and when we go back again, half of the class don't return. So maybe we'll just continue the way that you're going to do it. If you have the review one, you can always stop the recording and then continue on it. I'm worried there's only 6 of you. If we stop and then when we resume, only 3 will come back. It happened last time. Okay? Because the next part that we have here is involving a model that describes the behavior of the gases. So this is a kinetic molecular theory. Okay? So this kinetic molecular theory, this is a model that was developed by physicists to describe the behavior of gases. So this is based on the assumption that a gas consists of molecules moving in constant random motion. So the word itself is kinetic. So in chapter 6, kinetic energy is related to the mass and the velocity. So you're given this equation. But you don't need to memorize that equation. What's just telling you is that since there's large space between gases, they are constant random motion all the time. So the kinetic molecular theory, there are statements that describes the behavior of the gas. So these statements are what we call postulates. What it do is just describe the state, the behavior of the gases. So the first statement of the kinetic molecular theory that we have here, gases are composed of molecules whose sizes are negligible. Okay? So since they don't have definite shape and definite volume, you could say all the gases, their molecule sizes are negligible. Now these molecules, they move randomly in straight line in all directions and at various speeds. Okay? So what does it mean? Why do they move at various speeds? Maybe because of temperature. Maybe because also of the sizes. Okay? Although we say the sizes are negligible, but the sizes will still affect the speed of the molecules. So you expect the lighter molecules to move faster than the heavier molecules. Okay? Now, since there's a great distance between gas molecules or atoms, there's no such thing as what? Forces of attraction or repulsion between two molecules. They are very weak or negligible. Okay? Maybe there's some repulsion and attraction when the molecules collide, but it seldom happen because when molecules collide with one another, there's what we call elastic collision. Okay? There's no interaction. There's no, we could say, attraction or repulsion. What we say with the elastic, the energy of one molecule just transferred to the energy of the other molecule. And I'm going to show you what elastic collision is. Okay? And it says here, the most important part, the kinetic energy of the molecule is proportional to the absolute temperature. So these are the five, we could say, postulates of elastic collision. Okay? Now, what is this elastic collision that we're saying? So an elastic collision is in one in which no kinetic energy is lost. Just like this one. The collision on the left causes the ball on the right to swing the same height as the ball on the left had initially, with essentially no loss of kinetic energy. Okay? Now, molecular speed. According to the kinetic theory, the molecular speeds vary over a wide range of values. The main thing that dictates, we could say, molecular speed is temperature. Okay? Molecular speed increases as the temperature also increases. Just like us right now during this heat wave, we are restless. Okay? Now, if we're going to look at the relationship that we can have this so-called root mean square or the molecular speed. So this is a type of molecular speed that is equals to the speed of a molecule that has the average kinetic energy. Okay? So the root mean square that you have here, we could say that's this one. If you're going to look at these, two factors affect mu. And what's that? Temperature and molar mass. Okay? So one is directly proportional and one is indirectly proportional. I don't know if you can just uh, interpret if you have an equations like this one. So as you could see here, the temperature is directly proportional to the speed. The molar mass is indirectly proportional to the speed. Okay? So you can be given a calculation here. What is the RMS or the root mean square speed of carbon dioxide molecules in a container at 23 degrees Celsius? So you can, so if we're going to use that thing, mu equals to the square root 3 RT over the molar mass. Okay? So the way that you're going to use this one, this is an energetic problem. So the R is the 8.314. And this is just the 8.3145 that we usually use. We have to deal it with kilogram meter squared per second squared. That's joules, okay, per Kelvin. So you're going to replace it here. I have to spell out the unit that you have there because I want you to see what happened. So temperature to 23, so that's 296 Kelvin. Molar mass, CO2. So as you could see, you have a kilogram here. So you need to convert your 44 grams per mole into kilograms per mole. So that would be around what? 0.044? So kilograms meter squared per mole K, because you have the J, K mole. So if you're going to look at this, so this is the square root. So what the one that can be cancelled out? We can cancel the Kelvin, we can cancel the kilogram, we can cancel the mole, and what do you have? Meter squared over S squared. If you're going to get the square root of that, that's meters per second. And the corresponding value, which is all 4.1 times 10 to the 2. So I'm just showing you the unit of the root mean square as meters per second, which is the root, which is a unit of what we call speed. Okay. Try to do an operation here, but my focus here is on the principle. Okay. Now, what does this mean if you have, let's say, different temperature? So Maxwell predicted that the distribution of molecular speed at various temperatures would look like this. Okay. At 0 degrees Celsius, most of the speeds are here. But at 500 degrees Celsius, most of them are at a much higher speed compared to 0 degrees Celsius in terms of the distribution. This is Maxwell distribution. Okay, now the one that I want you to focus more is in this what we call effusion and diffusion. So when we're talking about diffusion, this is the process where the gas is spread out through another gas to occupy the space uniformly. So for instance here, you have what? Ammonia that diffuses through the air. How do we know we have an ammonia? We have a red litmus paper. So there's ammonia there. So when it forms into a gas, it converts or transforms your red litmus paper to blue due to the basic nature of the ammonia. Okay? So that is, we could say, diffusion. Another example of diffusion is if someone, let's say, put on a perfume and you smell, and the whole room would smell that fragrance of the perfume. That's another, we could say, process of diffusion. Now, how is it different from diffusion? Effusion. So effusion is a process by which gas flows through a small hole in a container. I don't know if you notice the balloon after some times. So the first time you ignite it, it will go usually to the ceiling. But after some time, it will just fall apart. You can just see them in the floor. Because what happened there, the gas would flow. And then after sometimes you see the balloon becoming smaller in volume. So that is what we call effusion. Now, the behavior of the gases here depends on the molar mass. Okay? How fast the molecule effuse or diffuse, okay, depends on the molar mass. So Thomas Graham has this law of effusion wherein he said at constant temperature and pressure, the rate of effusion of gas molecules through a particular hole is inversely proportional to the square root of the molecular mass of the gas. So what does it mean? The lighter the gas, the faster is the rate. The heavier is the gas, the slower is the rate of effusion. Okay? So for instance, if you have hydrogen and helium, which is used as buoyant gas in blimps, if there's a small leak between them, which gas would diffuse more and by what factor? So all you need to do is just, okay, I put the rate of the H2 over the rate of the HE. And then from that, I could put there the molar mass of the H2, 1 over the molar mass of the HE. But you can simplify this one. You can make this as the molar mass, okay, of HE over the molar mass of H2, the square root of that. Having that, you replace it with the molar mass. So what's the molar mass of HE? 4.00, right? And then H2 is around 2. So all you need to do is, what's the square root of 2? So what does 1.4 means? So for every time, okay, you have 1 for HE, H2 is moving at 1.4 times faster than your what we call HE. So if the HE just cover, let's say 1 centimeter, your H2 already covers 1.4 centimeter. Now we can replace this with another gas, let's say between oxygen and hydrogen. So which do you think is faster? So you expect this to be faster compared to this one. It's just like comparing, especially during this time of Olympic, Usain Bolt. You compare his speed, let's say against a sumo wrestler. So what's the difference between the two? One is lighter while the other one is heavier. So the speed of their movement, okay, will be affected. So that's what this law of effusion by Graham means. You can determine the factor, the speed factor that they have, the rate factor. So all you need to do is get the uh, reciprocal. So if I want you to compare, let's say CO2 versus O2, so if you're going to look at the rate, so you can put here the rate of CO2, and then this is the rate of O2. And if we're going to look at the factor here, what are we going to do? Okay, we just get the molar mass of your O2, which is 32, and then the CO2, which is 44. So if you're going to get the divide them, so you have here what? 0.73. Get the square root of that. So you have what? 0.85. So what does it mean? CO2 is at least 0.85 slower, or 0.85 times slower than oxygen. Now, if you want the CO2 to be the one that is relative to the oxygen, all you need to do is reverse it. And what you will have here is 44 over 32. And if you have 44 divided by 32, okay, So that's 1.375. You get the square root of that, so you will end up with 1.2. So what does this mean? Oxygen is 1.2 times faster, okay, compared to CO2 in terms of the rate. I hope you get that, because this is where you'll be asked the question. Okay. Now, the last part of the chapter that we have here, real gases. So what does it mean? All the while we're talking about what? Ideal gases. Where is ideal gases applicable? When you have low pressure and high temperature. What happens when there's low pressure? The gas are far from one another. What happens high temperature? The gas are far from one another. But we all know we don't live in an ideal world, right? We live in a real world. So the same thing with the gases. What happened at high pressure? So at high pressure, you deviate from ideality. Because ideality or ideal gases can only occur if you have low pressure. But at high pressure, what happened? The molecules become closer to one another, and there's such way that there's some interaction between them. Okay? So if you're going to look at the how gases behave, okay, ideal gas would behave like this one, but at low temperature. If you're going to apply high pressure, look what happened. They deviate from the ideal gas behavior. So this one here, that's where most of the gas can behave ideally, but once the pressure is increased, it doesn't behave ideally. So what happens? At high pressure, some of the kinetic molecular postulates no longer hold true. At high pressure, the volume of the gas molecules is not negligible. That's postulate 1. At high pressure, the intermolecular forces or postulates 3 are not negligible. So what do? Okay? You're going to at least put some correcting factor to your PB equals to nRT ideal gas equation. And we call it the van der Waals equation. But the way that they have here, so the P becomes B minus NB, and then the P becomes P plus N squared over A, N squared times A over B squared. And you are supposed to be given the values for this one. Okay? So we're just going to solve this thing, but we're not going to I'm not going to ask you a question about van der Waals equation. Maybe the way I ask you here is the principle, but not the calculation. Okay? So if you have this, using the van der Waals equation to calculate the pressure exerted by 2 mole of CO2, that is a volume of 10 liters, at 25 degrees Celsius. So compare this with the value with the pressure obtained from the ideal gas law. So how are we going to do it? PB equals to nRT. So to get the pressure, it's just nRT over B. And then we just put here 2.0821. And then what's the temperature? 25. So 25, that's 298 Kelvin divided by 10 liters. And the pressure that you have here would be around 4.89 atmosphere. Now, let's apply the van der Waals equation. So the pressure, if you're going to look at this, we're going to give you the value here. So 2.00 moles Oh, maybe what we can do is we can rearrange this thing here. So this one becomes, uh, you're going to divide it with b minus nb, so that cancel out, and you're going to have your minus n squared a over b squared. So if you're going to look at this, p is equals to nRT divided by b minus nb. Then you have this one minus n squared a. I think I didn't solve this in the other recording slides. That's why we're doing this here. So I can put here the 0.0821 liter atmosphere K mole, and then the 298 Kelvin. And then volume is still 10 liters, and then there's a corresponding value of that. So you have 2 moles, okay, and B is around 0.04286 liters per mole, while the other one, so you have the 2 moles squared, okay, and the A value is 3.656 liters squared atmosphere per mole squared, and you have 10 liters squared. So you try to see, can I cancel out the one that can be canceled? The answer is of course yes. Okay, liter, liter. So this is liters and this is small, so you can cancel that one. Then there's a liters there. And then for this one, so that's mole squared, liter squared, liter squared. So you have both atmosphere. So if you're going to put this, I get around 4933 atmosphere on this side, and on this side I have 0.146 atmosphere. And we're going to do it, you end up with 4.79. So see how the difference is. So that's when you take into consideration how what we call the real gas is different from ideal gas. Okay? So this is where we end this chapter. Question. So I'm going, do you want it to be open on Monday, or you want it to be open by the weekend? Anyone? Hello? So you can space your time. You know what I mean? Because you're going to retake. I'm allowing you to retake all chapters. So that means you can have 2 scores in your chapters. And if I need to use all of them to improve your grade, I'm going to do that. Is that okay with you? But I need to end it also with a certain time, because I want you to look over the 2 quizzes that you've taken in each chapter to see what's the correct answer to prepare you for the final exam. What can you say? So in the lab, today you're going to do experiment 12, and after that, by Wednesday, you're going to do experiment 8. We're not going to do experiment 9. We're just going to replace it with the home experiment that you're going to submit during the final exam, or earlier than the final exam if you're done. Are we okay on that? So if ever you miss chapter quizzes, you can take 2 quizzes again. I'll take care of that, because I can assure you the two quizzes that you're going to take, they don't have the same item or the same question. Yep, you're just going to do 4 out of 6 experiment, and I think there are some experiment there that is required, while the other one you can choose. If I'm not mistaken, I think the 2 experiments are required. Okay, the other one you can just mix it, and I think you have to start because some of them might take time, that like ripening of the thing. It will just be one lab reports. You just put what we call the portion of the different experiment. Even though you do 4 experiment there, but you're going to put everything in one lab report. And you go straight to the point, answering some of the guide questions that you have there. Okay? So if ever I wasn't able to open during the weekend the thing, just let me know. So any more question?